In this video, we're going to discuss polynomial division. We're going to think of this in the context of what we've already learned about, which is graphing polynomial functions. One of the key components of any graph is its x-intercepts, which are determined by finding the zeros of the function f of x. In other words, setting the function equal to 0 and solving for x. Zeros are easy to determine if the polynomial is already or can easily be factored. When it's more difficult to factor, we can use division to check possible factors. Keep in mind, what we think of as factoring is really just a special form of division. If something is a factor of a polynomial, it means that it divides in evenly to that polynomial. So we can rewrite the polynomial as a product of this factor that divides in evenly and then whatever's left after division. Remember, our ultimate goal is to solve an equation like f of x equals 0. But when we can't immediately factor using formulas and techniques we know, we can use division as a secondary method. So again, factoring is just a special form of division. When you think factor, think division. So we're going to divide polynomials just like we divide multi-digit numbers using long division. But before we try to divide with polynomials, let's review the long division procedure with numbers. Okay, so here's our example. So we want to divide 2,273 by 5. So if we want to set up for long division, here's our setup. We have 5 outside the division symbol, and we have 2,273 on the inside. The number on the outside, in this case 5, is called the divisor, and then the number on the inside, the number we're dividing into, is called the dividend. The answer to our problem, which is called the quotient, is going to go above the division symbol. So at each step in the division process, we divide the divisor into the smallest number it goes into fully. So in this case, the first thing that 5 divides into fully is going to be 22. In other words, the first 2 digits of our dividend. So 5 goes into 22 evenly 4 times. So I put 4 into the space for my quotient. We always line up our particular quotient value with the number we divided into. So in this case, it divides up with the second 2. Or excuse me, it lines up with the second 2. Now we're going to multiply our quotient by the divisor. So 4 times 5 is 20, and we're going to subtract whatever the result of that multiplication is. So essentially what we're doing when we do this is we're determining how much divided in evenly, and we're subtracting it out to see what's left over. So if we subtract this out, we're left with 273. Now, when you learned long division, you may have been taught just to subtract and then bring down one number from the dividend. We're actually going to bring down all the numbers each time, and the only reason I like to do this is so that we don't accidentally forget a number at the end. So you may have learned just to subtract, bring down the 2, and then bring down the 7 as well. Well, in this case, we're going to bring down both the 7 and the 3 so that we don't drop off anything at the end. Now we're going to repeat. So now 5 divides into 273. So the smallest part of that 5 divides into is going to be the 2 and the 7, so 27. 5 divides into 27 evenly 5 times, so 5 is going to be the next part of my quotient. Now I do the same thing I did before. So I multiply that part of the quotient by the divisor, and then I subtract. Once I subtract, I'm now left with 23. 5 divides into 23 4 times. 4 times 5 is 20, so I subtract my 20, and I'm left with a 3. If we have something left at the end of the problem, that's called the remainder. So 5 doesn't divide into 2,273 evenly. It divides in a certain amount, and then there's a portion left over, which again we call the remainder. So there's 2 ways we can interpret the solution to this problem. One way is to think of it as just a quotient with a remainder. So our quotient is 454. In other words, 5 times 454 is a certain amount that divides into 2,273, and then we have a remainder of 3. Or another way to think of it is as a mixed number. So 5 divides in evenly to 2,273 454 times, and then we have a fraction left over. So the whole part is 454. The fraction is formed by combining the remainder and the divisor. So what we're left with now is 3/5 of a whole unit that could divide into the dividend. So again, we can think of it in terms of just a discrete remainder by itself, or we can think of the remainder as being some fraction of the divisor. In other words, we're left with 3/5 that didn't divide in fully. So when we divide with polynomials, it's going to look basically the same as this, except our numbers are going to be replaced by algebraic expressions. But in terms of the procedure, it's going to be exactly the same. Although our procedure is going to be mostly the same for dividing with polynomials, we do have a couple of initial things we need to take care of. So when performing division with polynomials, we need to put in a zero placeholder wherever a term is missing. So we don't have to do this for our real number system because we automatically put in zeros when we don't have a particular value. So in our place value system, we automatically put in zeros if we don't have something non-zero to go there. However, when we're writing polynomials, if we skip a term, we skip a term. We don't have to put anything there. When we're dividing with polynomials, we need to make sure that any particular term that's missing has a zero in there. So suppose our highest exponent is a 2, and then we don't have a linear term or a term with an exponent of 1, we just have the quadratic term and then the constant term at the end. That means we would need to put in a zero placeholder for the particular term we're missing when we make sure everything's in order. We also need to list terms in order of their exponents, highest to lowest. So this is another thing that our place value system takes care of us. The highest place value is the highest place value, and we can assume that all the other digits are in the order they're supposed to be in for the particular number we're given. When we write polynomials, we can flip the order as long as our signs don't change, and we still have the same polynomial. So we need to make sure with our polynomial that we are actually writing things in order with our highest exponent first and then our lowest exponent last. So let's try one. So we have 6x cubed minus 5x squared minus 3 divided by 3x plus 2. So 6x cubed minus 5x squared minus 3 is our dividend, and then 3x plus 2 is our divisor. So first thing we need to do before we can set up our division and start dividing is check that all terms in both the dividend and the divisor are present and are in the correct order. So for our dividend, the thing we're dividing into, all the terms are in order, but we're missing a linear term. So we've got an x cubed, we've got an x squared, we should have an x there. So we need to put in a 0x in between our 5x squared and our 3. Now all the terms are present and they're in order, so we're good. For the divisor, the highest exponent is 1, so we have the linear term and we have the constant term. We have everything we need, so we're good. Now that we have everything we need, we can set it up for division. So we write it the exact same way we'd write it for long division. We write our divisor, what's dividing in, on the outside of the symbol, and then we write the dividend, what we're dividing into, on the inside of the division symbol. Just like with long division, we're taking the divisor and we have to recognize the smallest part the divisor divides into. Now notice for this one, the divisor has two parts. It has a 3x and a 2. All we care about is the 3x. So the 3x is what we're actually going to divide into. We're going to take care of the 2 as we go, but in terms of what's dividing into our dividend, 3x is what's dividing in. So the first thing the 3x divides into is the 6x cubed. So what I like to do is I like to go out to the side and actually write that individual division that I'm doing at each step. It's not as easy as just dividing in individual numbers into other individual numbers. Because we're dividing numbers and variables, it helps to kind of break this down into pieces and write extra work at each step. So for our first step, we're dividing 3x into 6x cubed. So the 6 divided by 3 gives us a 2. X cubed divided by x gives us an x squared. So we're left with 2x squared, and that's going to be the first portion of our quotient. Now, just like with long division, we take whatever we found for the quotient, we multiply it by our divisor, and then we put that under the dividend and we subtract. So 2x squared times 3x is going to be 6x cubed, and then 2x squared times 2 is going to be 4x squared. So I'm going to line each of those terms up underneath its matching term from the dividend, and then I'm subtracting all of that. So notice I put parentheses around the thing I'm subtracting. The reason I need to do that is because potentially, depending on what the sign is for the items I'm subtracting, subtraction may turn into addition. If I'm subtracting a negative, subtraction of a negative turns into addition. So we need to make sure that regardless of what the terms are, they're all being subtracted. One other thing I want you to notice is notice that the first terms, the 6x cubed, line up and will cancel. If you've done your division correctly, then that should happen every time. So the first term in the line should cancel out and all your x cubes should go away. You should only be left with everything that's x squared and below. So now let's subtract. So we've got a negative 5x squared minus a positive 4x squared, which is a negative 9x squared. And then just like before, we bring down everything else we're left with. Now we're dividing the 3x into the negative 9x squared. So just like before, I'm going to go out to the side and I'm going to do that little mini division problem separately, and then we'll put it back into the big problem. So negative 9 divided by 3 is going to be negative 3, and x squared divided by x is going to be x. So we're left with negative 3x, and that's going to be the next part of my quotient. Just like before, I multiply, I put it under my dividend, and then I subtract. Now be careful here because I'm multiplying by a negative 3x, not just a 3x. So I have to take into account that negative. Negative 3x times 3x is negative 9x squared. And then negative 3x times positive 2 is going to be negative 6x. So I'm going to line that up underneath my dividend. Notice now I definitely have a bunch of signs going on, so we're going to have to be really, really careful when we combine. Just like before, our first terms line up. They're the same, so they're going to cancel. So the negative 9x squareds are going to cancel out. I have a 0x, and I'm subtracting a negative 6x. So subtraction of a negative turns into addition. So 0x plus 6x is going to give me 6x. And then I bring down my 3. Finally, last step, 3x has to divide into 6x. So 6x divided by 3x. Well, our x's are going to cancel. 6 divided by 3 is 2. So 2 is going to be the last part of our quotient. Final step for multiplication and subtraction. So 2 times 3x is 6x. 2 times positive 2 is 4. So I'm subtracting 6x plus 4. The 6x's cancel. I have negative 3 minus a positive 4. So that's going to give me a negative 7. So in this case, I have a remainder of negative 7. So just like before, I have two ways I can write my quotient. I have the quotient and then I have a remainder. In this case, the remainder is negative 7. So I can write the quotient and the remainder separately. And then just like before, when we wrote the quotient and the remainder as a mixed number, in other words, we've got a whole number part, we've got a fractional part, we can do that here as well. It's just going to look a little different. So the quotient represents, in a sense, the whole number part. And then if you remember, we wrote the remainder as a fraction with the divisor. So we're going to do the same thing here, but because these are polynomials, these are things that are being added and subtracted, we need to make sure that what we're writing as the fraction with the remainder is actually added on to our polynomial. So we have our quotient, we have essentially our whole number part, and then the remainder is written as a fraction over the divisor, and we just tack that on the end with addition. So either of these is considered a reasonable way, an understandable way to write our quotient. The second part is going to be more valuable for us. It's going to give us more information because it also embeds whatever the divisor was into the problem. Let's try another one. So now we have a substantially longer division. We have a longer dividend. It looks like our divisor is the same length, but maybe it's going to be longer. Let's check and see. So remember, we've got to make sure that all terms are present and in the correct order. We've got to check this for the dividend and for the divisor. So in the dividend, everything's present. Notice our highest term is going to be an x to the fourth. We have an x to the fourth, an x cubed, and x squared, an x, and then a constant. So everything's present and accounted for, but the order is wrong. Everything is flipped. So we're going to have to flip the order so that our highest exponent is first, and then our constant term is last, and everything in the middle is ordered correctly. It looks like we're good after that. Now our divisor, we have an x squared and a constant, but we're missing the linear term in the middle. We're missing the x. So we need to put in a 0x placeholder. So once we've got all of that taken care of, now we can set up our division using these adjusted dividends and divisors. Just like before, we're dividing what's out front for our divisor into the first thing we can divide into in our dividend. So our first division using x squared is going to be 3x to the fourth divided by x squared. So x to the fourth divided by x squared is going to be x squared. The 3 doesn't divide by anything, so we leave it alone. So 3x squared is the first part of our quotient. Notice I'm going to line it up with the x squared term underneath in the dividend. Now I need to do my multiplication and then bring it down under the dividend and subtract. So 3x squared times x squared is going to be 3x to the fourth. 3x squared times 0x, this is a little different. So the 3 times 0 gives us a 0, but we still want to multiply the x's so that we know how to line this up. So 3 times 0 is 0, but the x squared times x gives us an x cubed. So we don't want to write just a 0, we're actually going to write a 0x cubed so that everything lines up the way we need it to line up. Then we have 3x squared times 2, so that's going to be 6x squared. So we put all those terms underneath our dividend and we subtract. Our first terms cancel, that's what we expect. We have 2x cubed minus 0x cubed. Those line up, but the 0 doesn't do anything, so we'll just bring down a 2x cubed. And then we have 4x squared minus 6x squared, which is going to give us a negative 2x squared. So 2x cubed, negative 2x squared, and then we bring down the rest of the problem. And now we're going to repeat, dividing x squared into 2x cubed. The x cubed and the x squared cancel to give us just a single x, and then 2 divides by 1, we're just left with 2. So the next portion of our quotient is going to be 2x. Now we repeat our multiplication. 2x times x squared is 2x cubed. 2x times 0x is 0x squared. And 2x times 2 is going to be 4x. So line those up underneath the respective terms and subtract all of that. First term cancels. Negative 2x squared is combined with 0x squared, so we just bring that one down. And then x minus a positive 4x is going to be negative 3x. So we have negative 2x squared minus 3x, and then we bring down that subtraction of 5 at the end. X squared now divides into negative 2x squared. So let's do this one. The x squareds are going to cancel, just leaving us with a negative 2. So the last part of our quotient is going to be negative 2. Multiply again. Negative 2 times x squared is negative 2x squared. Negative 2 times 0x is 0x again. And then negative 2 times 2 is going to be negative 4. So line all of these up. Our first terms cancel. And we're left with a remainder of negative 3x minus 1. So notice in this case that our remainder actually had 2 terms. If our divisor has 3 terms, then our remainder can have 2 terms. That's okay. How you know when you're done is the degree of what's left to be divided into is less than the degree of the divisor. So the last division we can do is an x squared divided into an x squared. Once we're left with something that's lower than an x squared, in this case it's x to the first power, we can't do any more division. So that's when we know we've reached our remainder and we can finish our problem. So we have our quotient, we have a remainder, we have 2 ways to write our answer. Either we write our quotient and just indicate what the remainder is by marking it with an R, or we write our quotient as a mixed number in a sense. So it's our quotient and then our remainder written as a fraction or a rational over the divisor. So notice the only thing we did here is when we rewrite the divisor, in other words, when we take the remainder and write it over the divisor, we're not going to put that 0x in there. The 0x is just a temporary placeholder to help our algebra, but of course we don't want to write zeros in a polynomial if we can avoid it. Now let's try one more and we should be set for long division. So we're dividing 2x squared plus 3x minus 14 by x minus 2. So let's check all our terms, make sure they're in the right order. Our dividend looks good. We have an x squared term, an x term, a constant term, and they're all in the same order correctly. And then our divisor looks good as well. So it looks like we can proceed with division without having to make any adjustments. So we're dividing x minus 2 into 2x squared plus 3x minus 14. Okay, so first division we're doing is x divided into 2x squared. So 2x squared divided by x squared divided by x is going to just leave us with a single x. So we have 2 times x. That's the first part of our quotient. We multiply and subtract. So we have 2x squared minus 4x and all of that is being subtracted from the dividend. So our first terms cancel. 3x minus a negative 4x, be careful with your signs here, that's the same thing as 3x plus 4x, so that's going to give us a 7x, and we bring down our subtracted 14. Then we're dividing x into 7x, so 7x divided by x, our x's cancel, we're just left with the 7. So 7 is going to be the other part of our quotient. Multiply and subtract, so 7 times x gives us 7x, and 7 times negative 2 is negative 14. So we're subtracting all of that, and in this case, what we multiplied by ended up being the same as what we were dividing into, so we're left with a remainder of 0. So in this case, our quotient can only be written in one form. It's 2x plus 7. So we have a special case here. Our divisor divided in evenly. We didn't have that happen before, but this time we did. The divisor divides in evenly. So when polynomial division results in a remainder of 0, it means that the divisor is a factor of the dividend. Remember, as we said before, factoring is just another way of saying division. It's a special way of saying division. So if our ultimate goal is to be able to factor, to write something like a long, complicated dividend as a bunch of smaller individual factors, then what we just determined is that x minus 2 is one of the factors that would divide into 2x squared plus 3x minus 14. As it turns out, the other factor is whatever we're left over with when we divide in, which in this case was 2x plus 7. So if we didn't know how to factor 2x squared plus 3x minus 14, we just showed that we can divide in x minus 2 evenly. It leaves us with a particular quotient, and so those two binomials, x minus 2 and 2x plus 7, give us our factorization for our quadratic. But before we get too deep into our discussion of factorization and solving equations, I want to teach you another way to divide when we're doing a division like the one we just did, of that specific form. So we call this synthetic division. We're doing the same thing that we did before, we're just kind of taking a shortcut so that our division problem doesn't take as long and we don't have to write as much. So synthetic division is a shortcut that can be used specifically and only when the divisor is of the form x minus a number. So if we have x plus a number, I want you to treat that as x minus a negative. So again, synthetic division only works when we're dividing in something of this form. The dividend can be any form we want, but the divisor has to specifically be a binomial of this form, x plus or minus a number. We need to keep in mind those placeholder and ordering rules. Those still apply for synthetic division. So we have to make sure before we do division in any type of form that we make sure our terms are in order, and that if we're missing a term, we put in a 0 placeholder. So since we know what the answer is to this problem, this is the one we just did, let's actually just redo this problem using our new type of division, our synthetic division. So this is how we would set up the long division. This is how we set up synthetic division. So this is going to take the place of the division symbol in our synthetic division. So we have a box in the top left-hand corner. Then we leave a little space under that and we draw a horizontal line. So that's our basic setup. That's where we're going to put our numbers in. So first thing we need to determine is what's going to go in the box. There's always going to be a number in the box. That's where our divisor goes. So what we're going to do is we're going to take our divisor and we're going to set it equal to 0 and solve for x. In this case, we find x equals 2. If you're thinking of x minus 2 as the factor we're checking, what we're putting into the box is whatever the 0 or the x-intercept would be corresponding to that particular factor. So in other words, if we were to take that factor and set it equal to 0, what would we get when we solve for x? So in this case, we get 2. 2 is what's going to go in the box. So in a sense, 2 is what we're dividing in. The other side, we're going to line up all the coefficients we have for our dividend. So this is where if we had a 0 placeholder, we'd also need to put that 0 placeholder in. So notice we have the exact same problem as above, but we don't have any x's. That's essentially the benefit of synthetic division. We do all the division we need to do, we do all the numerical components, we just don't have to worry about writing the variable over and over. So this is our basic setup, and we're just going to fill in other components as we go. So the procedure for synthetic division I like to think of as add vertically and multiply. We're going to take these two steps and we're going to repeat them over and over and over and over again, specifically using the values we got from the dividend, those coefficients we had from the dividend. So in each column, notice we've got 3 columns. If we don't think about the divisor as a column, we've got 3 columns, the 2 column, the 3 column, and the negative 14 column. In each of those columns, we're going to add vertically, and then we're going to multiply with the divisor with the number that's in the box. So this is what it's going to look like. So take the first column, the 2, the one outside the box, add vertically. Well, there's nothing to add with it, so essentially we're adding 0. In other words, we just bring down our 2. Then we're going to multiply. So whatever is underneath the horizontal line, I'm now going to multiply with whatever's in the box, and I'm going to put that underneath the next column. So in this case, I line it up under the 3. Then I'm going to add vertically again. So 3 plus 4 gives me 7. Then I'm going to multiply again. So 2 times 7 gives me 14. And that's going to go into the next column. And then I add vertically and I have a 0. And once I get down to the last column, I'm going to box that in with a vertical line. So what I found is the quotient that's on the left-hand side of that line, and the remainder is what's boxed in at the end. So of course we have x's. The x's need to come back somehow. This is when the x's are going to come back. So the actual quotient for the problem, which we discovered before, is 2x plus 7. Well, how do we know what x is to put back in, what the exponent should be, etc.? The quotient is always going to be 1 degree less than the dividend. So our dividend is degree 2, our highest exponent is 2. That means our quotient, whatever we're left over with, the highest exponent is going to be a 1. So we just go in order from term to term, going left to right, and we put in our x with our respective exponents going left to right, going highest to lowest. And then of course, if we have a remainder, we can tack it on just like we did before as a fraction over the divisor. So this is a great technique to use for division when we're specifically dividing in something of this form. It might take a little bit the first time, but once you've tried a lot of these, they go really, really fast, and they're clearly much faster than long division. Let's try another one. So now we want to do this particular division, and based on the form of the divisor, of the thing we're dividing in, we want to use synthetic division instead of long division. So just as before, we need to make sure we take care of the ordering of our terms, and we need to see if there need to be any placeholders put in before we put everything into the setup. So notice for our division, our highest exponent is 4. So we've got an x to the 4th, then we've got an x cubed. We're missing an x squared term, so we're going to need to add in a placeholder for that. Then we've got our linear term and we've got our constant. But everything is completely out of order. So when we set up this synthetic division, we're going to have to make sure to put all these terms in order from highest exponent to lowest exponent. So the number going in the box in this case is going to be a negative 2. If we take x plus 2, set it equal to 0, we get x equals negative 2. So that's what's going in the box. To the right of the box, we have a 1, a 4, a 0, a negative 2, and an 18. So remember, those are the coefficients we have from our dividend. The highest exponent term is x to the 4th. It doesn't have a coefficient, so we put a 1. The x cubed term has a coefficient of 4. We put in a placeholder for the x squared, so we're just going to put a 0 there. And then the linear term has a negative 2, and the constant at the end is 18. So this is our setup for synthetic division. Keep in mind, if you miss that placeholder, you will get a different answer. So the placeholder is absolutely essential. You have to make sure it's there before you start dividing. So again, add vertically, multiply, add vertically, multiply. We're going to do this over and over again for each of the columns. So for my first column, for the 1 column, there's nothing to add, so I just bring it down. Then I'm going to multiply with the divisor. In this case, negative 2 times 1 is negative 2, and that's going to go in the next column. 4 plus a negative 2 is 2. Negative 2 times 2 is negative 4. 0 plus a negative 4 is negative 4. Negative 2 times negative 4 is positive 8. Negative 2 plus 8 is positive 6. And then negative 2 times 6 is going to be negative 12. which leaves me with 6. I box in that last 6, and that is my remainder. So again, the numbers to the left of that vertical bar that I just drew, those give me the coefficients for my quotient. And then what's left in the end is my remainder. So my quotient, again, is going to be 1 degree less than my dividend. So my dividend, the degree was 4. It was an x to the 4th polynomial. So that means my quotient is going to start at x cubed. And the numbers that I have below the horizontal line give me the coefficients for each of the individual terms in my quotient, with that x cubed being my starting point. So I have x cubed plus 2x squared minus 4x plus 6. And then that remainder of 6 is tacked on the end as a fraction of the divisor. In this case, the divisor is x plus 2. So I'm adding on a 6 over x plus 2. So why do we care about this? Well, as we mentioned before, a number is a zero of a polynomial. In other words, it's one of the x-intercepts on that graph if the remainder from its synthetic division is 0. So if we perform division, in this case we've done synthetic, but even if we do long division, if we divide in and the remainder upon division is 0, then the number we divided in, or the factor we divided in, represents one of the x-intercepts on the graph of our particular polynomial in question. In this case, the polynomial is represented by the dividend, is what we're dividing in. So this also includes complex and irrational zeros. So the only things we've divided in so far have been integers. Well, of course, you know you can intersect the x-axis at places other than 0, 1, -1, etc. All those nice pretty numbers. We can have fractional intercepts as well. So we need to take into account the other types of intercepts we could have, the other types of zeros we have. The good news is we can still use synthetic division even with numbers other than the integers. So irrational zeros we'll worry about in a minute. Let's review complex numbers really quick though. So you should have at least briefly seen this in a previous math class. We're just going to glance at it. I'm just going to give you the basics of what we need to know. So the fundamental part of a complex number is the number I. I represents the square root of -1. So we've done some problems with square roots before, and as soon as we saw a square root with a negative underneath, we automatically said, okay, this is a problem, we can't have this. So typically it's when we're dealing with domain. We just said, okay, these particular numbers aren't part of the domain because they make the underneath of the square root negative. Well, now we're going to deal with those cases where whatever's underneath the square root is a negative number. So I is defined to represent the square root of -1. We call I the imaginary unit. It's essentially a number that mathematicians came up with to help them deal with that situation where we're trying to take a square root of a negative number and we know we can't do it. So here's a situation where we might want to use this. Say we want to figure out what the square root of -4 is. Well, immediately I say, okay, well, I can't do this. This is a problem. I've got a negative under the square root. Well, that's true and it's not true. So if we wanted to graph this number somewhere on the coordinate plane, then that's correct. There's nothing we can do with this. This doesn't exist on our standard coordinate plane using our standard real number system. However, say we want to use this in a particular problem. So let's just deal with it, considering that we have a way to deal with it. What I do notice is that if I didn't have that negative, I could take the square root of 4 just fine. It wouldn't be a problem. The problem is the negative. So what I'm going to do is I'm going to take that -4 and I'm going to split it up into two parts. I'm going to split it up into the 4, the thing that I could easily take the square root of, and the -1, the thing that's giving me a problem. So one of the rules with square roots is that if we're taking a square root of two things that are being multiplied together, then we can split it up into two separate square roots. We can take each individual square root separately. So we use this property to simplify complicated square roots. We split it up into something we can take the square root of, and then we have a square root of just things that are left over that we can't simplify. So square root of 4 is going to be 2, and then based on this number I that we've just defined, square root of -1, the thing that was initially giving us a problem, is actually going to be I. So this all simplifies down to 2 times I, which is what we call an imaginary number. So a complex number is a combination of an imaginary part like this 2i and then a real number, like in this case the number 1. So 1 plus 2i is considered to be a complex number. 1 is the real part, so it doesn't have an I tacked onto it. If we were to try to graph 1, the number 1 is a real number. It exists somewhere on our coordinate plane and we're fine with it. 2, specifically the coefficient for the I, 2 is considered to be the imaginary part. So it's the part of the complex number that's tacked onto I. If we graph complex numbers, which believe it or not we can actually do, we graph them in what we call the complex plane. So the x-axis now becomes the real numbers, and then the y-axis now becomes the imaginary numbers. So we would graph this essentially like we graph the point 1, 2, x-coordinate of 1, y-coordinate of 2. We would graph a complex number like this in basically the same way. You don't need to worry about that too much. For our purposes, just recognize we know what I is. I is the square root of -1, and it allows us to deal with square roots of negatives. So what we want to do now is we want to use synthetic division to determine if some number that we're given is a zero of a polynomial. In other words, if it represents an x-intercept from that polynomial, if we were to graph it in the coordinate plane. So we're going to do this with pretty numbers, and we're also going to try this with irrational numbers and complex numbers. So let's try a few. So here's our first problem. We want to use the remainder theorem, in other words, that rule that if the remainder is 0, something is a 0, to determine if the number we're given is a 0 of the polynomial we're given. So here's our polynomial, and we're given the number c equals 4 to check. So we want to see if the number 4 is a 0 of this polynomial. In other words, if we were to graph this polynomial, is 4 going to be one of our x-intercepts? That's what we want to determine. So we can determine this using synthetic division. So 4 is going to go into the box. My dividend looks good. It looks like I've got all my terms. They're all in order. So I just put my coefficients to the right of that. Add vertically and multiply. Remember, that's our procedure. So we bring down our 2. 4 times 2 is 8. -4 plus 8 is 4. 4 times 4 is 16. -13 plus 16 is 3. And then 4 times 3 is 12. -9 plus 12 gives us 3. So we have a remainder of 3. So by that rule we just talked about, we need to have a remainder of 0 in order to know that this particular number divided in evenly, that it generates a factor, that it represents an x-intercept. So because our remainder was not 0, c equals 4 is not a 0 of f of x. In other words, 4 would not be one of our x-intercepts were we to graph this particular polynomial. Now let's try one with an irrational number. So we have a new polynomial, new dividend, and we're going to check it with square root of 3, which is an irrational number. If we were to plug that into the calculator, we'd get a really long decimal, and it turns out that decimal would actually be an approximation. Square root of 3 is as exact as it gets. There's nothing we can do with it. But the procedure is the same, so we're dividing in square root of 3. For this one, make sure you leave yourself some space when you draw your setup for synthetic division. Make sure you leave some space between the numbers above the horizontal line. So all of our terms are there. They're all in the correct order. We can just bring down our coefficients and we can get started. So I bring down my 1. 1 times square root of 3, well, anything times 1 is going to be itself. So 1 times square root of 3 is going to be the square root of 3. Okay, so now I'm combining 1, which is an integer, it's a rational number, with the square root of 3, which is an irrational number. So we can't lump them together into one term, so we just write it as 1 plus the square root of 3. There's no other way to write it so that it's simpler. So 1 plus the square root of 3. Now we need to multiply. So because this is a little bit more involved, this actually involves some distribution. The -3 is multiplied by a couple different things. I like to go out to the side and actually do the multiplication on its own, and then we'll take it and put it back in the problem. So we're multiplying square root of 3 times 1 plus the square root of 3. So we have to distribute that square root to both of the terms in parentheses. That gives us square root of 3 plus the square root of 3 squared. So notice square root of 3 times itself, that's squaring a square root. So square root of 3 we can't simplify. However, the one that's squared, anytime a square root is squared, anytime one is applied to the other, they cancel each other out. So I'm left with the square root of 3 plus 3. And again, that's as simple as it goes, so that's what goes back into our problem. So now I'm combining negative 3 with this number I just found. Well, I can combine the negative 3 and the 3 because those are both rational parts. I can't do anything specific with the square root of 3, so I just leave that alone. The negative 3 and the positive 3, turns out, are going to cancel. So I'm just left with the square root of 3. Then I have one more multiplication, so the square root of 3 times the square root of 3. Well, we already decided if we multiply a square root by itself, if we square it, the square root is going to go away, and we're just going to be left with whatever was under the square root. In this case, it's 3. Then I combine vertically one last time. Negative 3 plus 3 gives me 0. So my remainder from this synthetic division is 0. Because my remainder is 0, that means the number square root of 3 is a 0 of this polynomial. So whatever that number is, if we were to approximate it, we would get a sense of what that number roughly is. That's going to be one of our x-intercepts if we were to graph this polynomial in the coordinate plane. So keep in mind, there are plenty of times when your x-intercepts are not going to be nice integer or even fractional numbers. You may have intercepts that are going to be irrational numbers. So that's something we have to deal with as it comes. This is one way to check whether or not an irrational number is going to be one of your x-intercepts. Now let's try one more. So let's try a complex number. So we've got our polynomial, we've got our dividend. We're dividing in the complex number 1 plus 2i. So that was the one we saw from before. So the real part is 1, the imaginary part is 2. We're adding those together and we get a complex number. So notice for our dividend, it looks like we're missing a term. We're missing the x squared term. So we're going to have to put in a 0 placeholder when we set up our synthetic division. So 1 plus 2i is going to go in the box. And then our coefficients, including that 0 placeholder, are going to go out to the right. Just like with the irrational number, make sure you leave yourself a bunch of space with this. This is going to take up a little more space than normal synthetic division. Procedure's the same, so bring down your 1. Anything times 1 is going to be itself. So 1 plus 2i times 1 is just going to be 1 plus 2i, so that goes into my next column. I'm combining this, whatever this number is, 1 plus 2i, with a 0. So I just have my 1 plus 2i. Here's where it gets interesting. So now I need to multiply. So let's go out to the side and do this multiplication. It's the divisor, 1 plus 2i, times whatever's under the bar, which happens in this case to also be 1 plus 2i. So I'm multiplying essentially two binomials together. I have to multiply by FOIL. Remember, first, outer, inner, last. So I'm multiplying 4 times here. I'm going to get 4 terms. So 1 times 1 is 1. That's my first terms. My outer terms, 1 times 2i is going to be 2i. Inner terms, 2i times 1 is going to be 2i. And then last terms, 2i times 2i, multiply these separate parts together, that gives us 4i squared. So just foiling, this is what we get. Now we want to see what else we can simplify. So the 2i's can definitely combine together. That'll give us 4i. Think of them like terms. You can treat I like a variable in a sense. It behaves basically the same way. Now what about that I squared on the end? Well, if I is the square root of negative 1, then squaring that square root is just going to leave us with a negative 1. So if we make those two simplifications, we have 1 plus 4i plus 4 times now negative 1. I squared is going to be negative 1, again, because I is the square root of negative 1. If we square that square root, the square root goes away. So we can multiply that 4 times negative 1. That gives us negative 4. Combine it with the 1 out front, and that's negative 3 plus 4i. So that's what's going to go back into our problem. That's fully simplified. Combining vertically, the 1 and the negative 3 can combine together, so that's going to give us negative 2 plus 4i. Now we're in another spot where we need to go out to the side and multiply. So again, two binomials, in this case they're different. We have 4 multiplications, first, outer, inner, last. So multiply all those out, and this is what we should get. Now our goal is to simplify. So notice we have a positive 4i and a negative 4i. Those terms are equal and opposite, so they're going to cancel. We already decided that I squared is the square root of negative 1 squared. So the square root goes away and we're just left with a negative 1. So if we simplify this down, we have negative 2 plus 8 times negative 1. 8 times negative 1 is negative 8. Negative 2 plus a negative 8 is going to be a negative 10. So notice in this case, just based on how everything worked out, the i's completely went away and we ended up with entirely real numbers at the end. So the negative 10 goes back into my problem. I add again and my remainder is 0. So because my remainder is 0 from this synthetic division, 1 plus 2i, the complex number 1 plus 2i, is a 0 of f of x. Now this is a slightly different situation from the two we just looked at. As we've already mentioned, 1 plus 2i is not something on our standard coordinate plane. It can be graphed in a special situation on a special coordinate plane, but our standard situation with the x and y axis, 1 plus 2i doesn't exist anywhere on there. So although this is a 0 of the polynomial, this is something that divides into our polynomial, it doesn't actually represent an x-intercept. So dividing it in makes our lives easier because it reduces the polynomial to something smaller, something that's more manageable to work with. We might be able to continue and potentially find some actual x-intercepts, but even though this number divides in, because it doesn't exist anywhere on the coordinate plane, it doesn't actually correspond to an x-intercept. So that's just something to keep in mind. Irrational numbers can give us x-intercepts. Complex numbers do not give us x-intercepts, even if they are zeros of our polynomial. So let's wrap up this section by putting all of this together. So just to recap, to say that a number represented by the variable c is a 0 of f of x equates to saying that x minus c is a factor of f of x. So if you think back to what we said in the beginning, the goal is to fully factor f of x. We want to get all these individual factors so that we can set each factor equal to 0, which will give us all of our x-intercepts, which are one of the key components of a graph of our function. So if we can take a particular number and it divides in evenly using synthetic division, then that means two things. It means we found an x-intercept, assuming it is something that's not a complex number, assuming it's not something that has that I in it. We found an x-intercept, and two, we found one of the factors that divides into our particular function that we want to, at least in theory, graph. So this means that a polynomial can be partially factored using synthetic division. Once we find something that divides in evenly, we found one of the factors. Then we can complete the factorization using other techniques. And this is going to allow us to find all our zeros, all our x-intercepts for our polynomial, regardless of how high the exponent is. So the reason we need this is because we have techniques to factor quadratics. We even have some techniques to factor special cases when we have a highest exponent of 3. But for anything above that, we don't really have any formulas we can use to factor. We don't have the quadratic formula. We don't have standard factoring procedures. This is really best case. All we can really do is see if things divide into our polynomial, and maybe we get lucky. If something divides in, then that gives us a starting point. So if we can get that starting point, then we can find something that divides in. We can take the quotient and just use what's left over after division, and we continue factoring, we continue dividing from that point. Okay, so let's do it. So let's do an entire problem from start to finish. We've got a polynomial. We want to fully factor it using division. So we're only going to do one because we're going to do a bunch of these kind of problems in the next section, but I just want to give you a sense of what this is going to look like. What's the general procedure? What's the goal? What's the... Okay, so let's try one. So we want to put everything together. So general idea is, imagine we're trying to graph a particular polynomial. So we can find our end behavior, but we need to find our x-intercepts. So we take our polynomial, we set it equal to 0, and we've got to factor it. So we're now to the point where we want to factor. So here's our polynomial. This is conceptually the polynomial we want to graph. We want to find its x-intercepts. So first thing we want to do is we want to factor this polynomial given the piece of information that -5 is a zero of this polynomial. So notice this is a cubic polynomial. We do have some techniques to factor cubes, but this one probably can't be factored using any special techniques. So in the absence of any other information, the only thing we really have is division. We have to try dividing things in using synthetic division. Well, the good news is we were already given something that we're told is supposed to divide in evenly. Telling us that -5 is a zero of this polynomial tells us two things. It tells us -5 divides in evenly, and that -5 is one of our x-intercepts. So why does this matter? They've told us that it's one of the intercepts. How are we going to use it? Well, we divide in -5 using synthetic division, and the reason this helps us is because once we divide this in, the quotient, what we get after we divide, is going to be a polynomial that's smaller and that's more manageable, something that we may be able to continue to factor. So the goal is to use synthetic division as long as we need to until we get to something that we know how to factor, and then we can combine our synthetic division and our factoring to figure out all the x-intercepts for our particular polynomial that supposedly we're trying to graph. So we're setting it up with synthetic division. -5 goes in the box. It looks like we've got all our terms. They're all in the right order, so I can just write my coefficients down. So bring my 3 down. -5 times 3 is -15. 25 and -15 is 10. -5 and 10 is -50. 42 and -50 is -8. And then -5 and -8 is 40. So I combine and I get a remainder of 0. No surprise there. That's what I was told I was going to get. Why I care is because now I've got the quotient. My quotient, the part that still contains the rest of the x-intercepts, is 3x squared plus 10x minus 8. So the good news is that the quotient is quadratic. Regardless of how bad a quadratic we get, we know we have techniques to deal with quadratics. Best case, we factor. Worst case, we use the quadratic formula. In either case, we will find our x-intercepts if there are any more x-intercepts to be found. So it turns out that this one actually factors. So let's review factoring a little bit. Let's actually factor this one using a particular factoring technique. So what I'm going to use is called the X method, or some people call it the AC method. So I'm going to draw a big X, and this is just a diagram to break down the pieces of the problem and analyze it a little bit more. So what goes in the top of X is going to be the leading coefficient multiplied by the constant term. So in this case, it's 3 times -8, which is -24. What goes in the bottom of the X is going to be the middle coefficient, in this case 10. So I need to fill in the other two parts of the X, and I'm going to fill it in with two separate numbers. How do I find them? Well, these are numbers that multiply to give me -24, but also add to give me a positive 10. So because they multiply to give me a negative, I know they have to be opposite in sign. So one is going to be negative, one's going to be positive. But they also have to add at the same time to give me a positive 10. So this is really trial and error at this point. The best way to see if you can figure out what the two numbers are, if you don't immediately see it, is to write down all the different ways you could factor -24 as a positive number times a negative number. It turns out the only possible factorization that also adds to give a positive 10 is going to be -2 and positive 12. And if I have a negative and a positive, I like to write the negative on the left-hand side and the positive on the right-hand side. There's a reason for that I'll show you in just a second. So these are the unique paired numbers that multiply to give -24 and add to give 10. So what I'm going to do is I'm going to take 10x, I'm going to take that term in the center of my quadratic, and I'm going to split it up using the numbers -2 and 12. So I'm going to rewrite this polynomial that has 3 terms with 4 terms. I'm taking that 10x and I'm writing it as -2x and positive 12x. The reason I'm doing this is because there's a specific technique for factoring called grouping. Grouping requires 4 terms, so I'm splitting this quadratic that has 3 terms up into something with 4 terms very strategically. So in grouping, we look at the first 2 terms and the last 2 terms, and we want to factor the greatest common factor out of each of those individual pairs. So the first pair, the only thing they have in common is an x. So I can factor an x out of the first pair. For the second pair, they have in common a 4, so I can factor out a 4. So for each of those pairs, I factor out whatever the GCF is for that, and then I leave what's left just for that pair. So the reason I like to put the negative first and the positive second is because now the pairs have a plus sign in between them, so we don't have to worry so much about any issues with sign when we're factoring. So as long as I can put a plus sign smack dab in the middle, I don't have to worry about whether I'm factoring a positive or negative and whether it changes signs. It just makes my life a lot easier. So one thing to notice once we've factored out our greatest common factor from each pair is what's left in parentheses is the same for the first pair and for the second pair. We had a 3x minus 2 left over with both. That is not a coincidence. That's why we factor this way. We expect that to happen. So now what I have is one big term out front and one big term on the end. They each have a 3x minus 2 in common. So now I can factor that 3x minus 2 out of the whole problem. And from the first term, I'm left with an x. From the second, I'm left with a 4. So I now have my full factorization, 3x minus 2 times x plus 4. So if I put it all together, they've told me that negative 5 is a 0, so the factor that goes with negative 5 is going to be x plus 5. That's what I would set equal to 0 to solve for x equals negative 5. I can put together all my factors, and I have a full factorization for f of x. So f of x is going to be x plus 5 times 3x minus 2 times x plus 4. So now let's take it one step further. So we factored it. Now we want to use our factorization to solve f of x equals 0. In other words, to solve for the zeros of f, find our x-intercepts. So we're finding the x-intercepts by solving this equation. Zeros and x-intercepts mean the same thing, essentially. So we take our factorization and set it equal to 0. If I were to take each individual factor and set it equal to 0, my x-intercepts are negative 5, negative 4, and positive 2/3. So if I were to graph this polynomial, these would be my 3 x-intercepts. These would be my only intercepts. Combine it with end behavior, and I've got my full graph. So let's summarize what we've seen in this video. So all polynomials can be divided using a technique similar to that used for long division. This can work for any pair of polynomials regardless of what form the divisor is in. Long division is always an option, and it looks basically the same as old school long division that you learned in elementary school. When the divisor is specifically of the form x minus a number or x plus a number, we can use synthetic division instead of long division. It gives us the same result, but in about half the time, and I feel like overall, I personally am less likely to make a mistake doing synthetic division than I am with long division, just because we don't have to worry so much about keeping track of signs and making sure that all the terms are lined up correctly. Overall, synthetic division is easier, but keep in mind, you can only use synthetic division when you're specifically dividing in a divisor of the form x plus or minus a number. So just keep that in mind. And then why do we care about this? Well, if the result of division is a remainder of 0, then we know that the divisor is a factor of the dividend. It's something that divides in evenly. If we were to try to factor this big polynomial represented by the dividend, whatever we divided in would be one of the factors. And then the associated 0 we get from that factor is going to be one of the x-intercepts of the dividend. So if you remember, x-intercepts, end behavior, those are the two major components we use to graph any polynomial function. This is just one technique we can use to help us find the x-intercepts when our particular polynomial is more complicated.